1 March, 1954. 70 miles from the first shot of Operation Castle. A device with 1,000 times the energy of the bomb that shattered Hiroshima, exceeding the power of that bomb as vastly as it exceeded the greatest high-explosive giants of World War II. Multi-megaton weapons are here, stockpile items as of today, with potentialities that compel revision of previous military concepts. But without full knowledge of those potentialities, intelligent revision is impossible. To gain such knowledge, the Armed Forces Special Weapons Project conducted extensive military effects tests for the three services during Castle. The data obtained will serve as factual tools to shape our strategic and tactical planning to warfare's new dimensions, a transition which will take us from the familiar ground of low-yield capabilities into an era of new problems as well as new power. Castle was a two-atoll operation because the program was too big and the devices too powerful for convenient staging at a single atoll as in the past. 5 of the 6 Castle shots were fired at Bikini Atoll, 2 near Namu Island, 2 on barges in the north side of the lagoon, and 1 shot down on Inanman Island. At Eniwetok Atoll, some 200 miles to the west, only 1 shot was fired, number 6, on a barge in the old Ivy Mike crater. Ground space in the Pacific Proving Grounds is scanty in the form of small islands, and many of Castle's projects were handicapped by this fact. For one thing, it was not practical in most cases to lay out instrument lines involving runs over dry land alone for any sizable distances. It should also be remembered that all Castle shots, like Ivy Mike, were surface bursts. 2 of them fired in ground surface cabs, and the other 4 fired on barges. We therefore do not as yet have any empirical data on effects of multi-megaton air bursts. Looking now at the data we did obtain, we may first consider the nuclear radiation aspects. Initial gamma measurements on this operation employed orthodox techniques with chemical and film dosimeters and scintillation detectors at a number of island and reef stations. These studies confirmed Ivy Mike's indications that initial gamma from a high-yield device differs considerably in delivery timing from that of a weapon in the kiloton range. Roughly 50% of the initial gamma dose from kiloton weapons arrives within the first half-second after the burst, allowing no time for target personnel to take cover. With a multi-megaton bomb, however, some 80 or 90% of initial gamma will not arrive on target until after arrival of the shock front. At fair distances, this could provide a number of seconds for target personnel to take such cover as may be available. This timing differential becomes of academic interest only in view of another Castle finding. It developed that initial gamma dosage at ranges of concern reached only about 1/10 of the predicted levels. This means that initial gamma from the big weapons drops off to military unimportance at ranges at which blast and thermal will still cause almost 100% casualties outside of heavy bunkers. Measurement of neutron spectrum and flux were made indirectly by study of nuclear changes in threshold detector elements exposed on sample mounts at various distances. It developed that the neutron flux, while heavy, attenuated so rapidly with distance that in comparison to other effects, it too may be considered to have little military value. We come next to a field in which the radiological effects of megaton surface bursts are far from negligible, are, in fact, of profound importance. Ever since the 1 kiloton surface burst of Jangle in Nevada, we have recognized that such bursts may produce widespread residual contamination of significant intensity. Limited investigation on Ivy gave us scanty data, so our biggest Castle project was in this area. Further knowledge was a military necessity as well as grimly relevant to the defense of American cities. It is worth emphasis that only surface or subsurface bursts produce important fallout, and for the moment we will consider only land surface bursts reasonably approximated by the first Castle shot. The seawater involved in this fireball did not significantly alter the radiation levels or distribution of local fallout from what would be expected of a land surface burst. Fallout history begins with the scores of millions of tons of earth vaporized by such a detonation. This material, which rises with the fireball, has neither original nor induced radioactivity of any consequence. But during condensation, it traps radioactive bomb products significant for intense gamma emission. In the first few minutes, the visible cloud will reach from 60 to 100,000 feet or more for multi-megaton bursts, with a stem over 5 miles in diameter. Fallout of the radioactive particles inside and below the visible structure now begins, through the operation of gravity, rainout, convection, and other mechanisms. The active airborne particles move on downwind, causing significant fallout for a period of 10 hours or more. The settling dust reaches ground in a pattern which, while naturally quite variable, is reasonably represented as a long leaf shape. Starting back at the time of burst again, it is important to note that while the visible cloud will move with cloud height winds, the fallout particles will settle through lower winds of possibly conflicting directions at various heights. Orientation of the ground fallout pattern is determined by a resultant wind vector which is an average of all winds from ground to cloud height. Therefore, the fallout pattern may take an entirely different path from that of the visible cloud. Changes in the average wind vector as the falling dust moves across country can cause major distortion of the fallout pattern. The most important collectors of Castle fallout data were of two main types: total collectors, such as the gum paper trays and funnels of several sizes; intermittent collectors, such as belt samplers; and the rotating drums, both of which exposed collection trays at timed intervals. Such instrumentation in varying combinations was placed on a number of islands at Bikini and more distant atolls. Since this constituted scanty coverage, 26 instrumented stations were located on anchored rafts a few miles apart throughout the Bikini Lagoon. Losses of this type of equipment were heavy on the unexpectedly powerful first shot, which only 12 of the 26 stations survived. All those within a 10-mile radius were overturned. For the final shot, number 6 in the old Mike crater, a similar grid of 32 of these raft stations was employed to document the Eniwetok Lagoon. To extend the coverage outside the lagoons, original planning called for the use of floating Dan buoys in concentric rings at 30 to 100 miles from ground zero. They were instrumented with funnel and sticky paper collectors, plus small radio transmitters to assist in locating them after each shot. Success of the Dan buoy project was limited by difficulty of recovery due to high seas and change of shot schedules. On the last two shots, open ocean fallout was documented by a new technique of water survey and sampling methods. 1-gallon water samples were taken at a number of stations in contaminated areas at various depths from the surface to several hundred meters down. Further data were obtained from surface and underwater gamma meters, either lowered straight down for determination of radiation versus depth, or towed behind ships for contour surveys. Vertical profile data from the meters and from analysis of the water samples indicated that the radioactive debris mixes rapidly and uniformly throughout the surface layer down to the thermocline at around 120 meters. This vertical mixing information made it possible to estimate total fallout intensity at a given ocean site by measuring the activity of a single sample of surface water from that spot. All computations were correlated with the data from buoy and raft stations, ships, and island weather stations. In fact, emphasis on this open ocean survey resulted directly from the unforeseen fallout from Shot 1 on some populated distant islands, a weather station on one of them. These islands, functioning as accidental total fallout collectors, gave us our first real clues to the vast area affected by contamination from a high-yield surface burst. Within a few hours after that shot, a powdery snow-like fallout began on Ilinganai and Rongelap atolls, then on Rongerik, and finally on Uterik. By 8 plus 78 hours, 229 Marshall Islanders and 28 American service personnel were evacuated to Kwajalein for survey and treatment. It was tentatively estimated that the total gamma dose may have approached 70 Roentgens for the people on Ilinganai, 175 Roentgens for some on southern Rongelap, 80 on Rongerik, and only 14 on Uterik. The dosages in these outer fringe areas did not appear to reach levels of immediate combat significance, nor did any severely incapacitating effects show up during treatment or observation on Kwajalein in excess of 40 days. A majority of those receiving the heaviest radiation reported some transient nausea on the first or second day, and there was a small incidence of gastrointestinal disturbances of short duration. Some loss of hair was a frequent symptom. Most of the Marshallese in this category developed multiple skin lesions, usually not severe, predominantly on the scalp, back of the neck, and feet. Only a few developed mild secondary infections during healing. The lesions appeared to be directly related to the amount of fallout deposited on the skin rather than to the generalized whole-body radiation. It appeared that even one layer of clothing afforded substantial skin protection, suggesting that the beta energies of the fallout material were relatively low. Significant blood changes were found in patients from the heavier fallout areas, including pronounced lowering of both platelet and leukocyte counts, which would reduce the body's ability to combat hemorrhage or infection. Returns to normal were not complete after 6 weeks. Subsequent surveys of the fallout islands, together with autopsies of domestic animals, have indicated that intake of contaminants through the lungs in cases of this sort will be negligible compared to the external radiation dose, and will probably be negligible in comparison with the intake with food and water unless these supplies are protected. Possibly some new Air Force equipment. We can now take another look at the fallout material that came down on Rongelat. The small portion of the cloud material destined for southern Rongelat, where the natives lived, was emitting gamma at the rate of about 130 Roentgens per hour at H+1, or 1 hour after the shot. Decaying with time as it traveled another 4 hours downwind, the material was emitting perhaps 20 Roentgens per hour, and still decaying when it grounded at Rongelat, 100 miles from zero. By evacuation time at H+50 hours, the maximum accumulated dose at that point was around 175 Roentgens, a mild sickness dose for less than 50% of exposed personnel. The activity increased rapidly toward the uninhabited north, however, and in 10 miles reached a mean lethal level for exposed humans on the order of 450 Roentgens. On the atoll's upper islands, this H+5 to H+50 hour dosage ran from possibly 1,500 to 3,000 Roentgens, well above the lethal human dose. We can plot a line of peak observed readings, but considering the average wind vector, the center line of the fallout was apparently still farther north. Mapping from a few established values, we can at least approximate the minimum fallout pattern. The contours are selected to represent accumulated dosage from arrival time to H+50 hours. The 450 Roentgen mean lethal dose appears to have enclosed an area exceeding 7,000 statute square miles, an area some 250 miles long, an area which on land could blanket large segments of population. And note that inside this 450 Roentgen border, the dose accumulated by H+50 hours climbs quickly to 100% lethal for exposed humans. On the defensive side, it should be remembered that the gamma intensity of fallout at H+7 hours has decayed to 1/10 what it was at H+1, and by H+48 hours, it is only 1/100th of the H+1 value. Additionally, the shelter of a frame dwelling will cut the dose rate to 1/2 of the outside rate, and a position in the basement would reduce it to 1/10. Attenuations in excess of 1,000 can be gained in basements or middle stories of multi-story buildings, or in simple shelters with at least 3 feet of earth overhead. In general, however, it should be recognized that the best average shelter available in cities will cut dose rates only to a level between 1/4 and 1/8 of the full dose. Immediate evacuation when fallout begins is not too promising, both because of sheer physical difficulties and because of probable lack of data as to safe and dangerous areas. The most practical solution appears to be the widespread use of available shelter for 2 to 4 days before attempting mass evacuation. We will consider now a phase of the fallout studies which was of major importance to naval operations. This was an experiment with a pair of modified Liberty ships to determine the effectiveness of a saltwater spray system designed to wash contamination from weather surfaces as a ship progresses through a heavy fallout area. Additional studies were made of the effectiveness of decks and other ship structures for shielding interior locations and of the entry of airborne contaminants through ventilation and boiler air systems. The Liberty ships designated as vehicles for these and related studies were YAG-39, fully equipped with a washdown system, and YAG-40 with no washdown. Each ship's modifications included a representative flight deck, 2 gun installations, and an F-4U aircraft carried aft. Both ships were heavily instrumented to measure gamma dose rate and total dosage. On each of the 4 shots participated in, an average of 400 detector channels was in operation, transmitting data below decks to the recording rooms. Airborne and weather deck beta distribution studies were also accomplished. The ships were equipped with drone control systems for remote operation of engines, steering, and the washdown apparatus of YAG-39. During the first 2 shots, both ships were unmanned in their maneuvers into the fallout region and were controlled from a P-2V-5 aircraft with a secondary control center aboard the carrier Bairoko. During the remaining shots on which the project was active, shots 4 and 5, YAG-39 was manned by a small crew which controlled the ship from a well-shielded compartment. This party in turn exercised radio control of the nearby YAG-40. During these exposures to heavy fallout, the flow rate of YAG-39's washdown was approximately 2,000 gallons per minute. Radiation levels below decks remained low enough to permit the crew to take the ship back to Eniwetok Lagoon after each shot. YAG-40, unprotected by washdown, could not be manned for the return trip. After each test period, radio control was dropped and the ship was towed back to Eniwetok. At Eniwetok, the F-4U airplanes were removed to shore for further study and cleaning operations. Comparisons of radiation data on the 2 YAGs led to an estimate that washdown effectiveness on ships and their exposed aircraft will average about 95% based on the dose rate. Shielding studies indicated that weather deck gamma levels will be attenuated by distance and structural shielding to a fraction estimated at 2/10 in compartments close to the weather surfaces and approximately 1/1000th in interior compartments below armored decks. Boiler air system contamination appeared to be minor, and the mushroom heads on ventilation intakes reduced the airborne gamma contamination below decks by 99%. Stopping the fans made no apparent difference. Some Shot 5 figures will give a rough idea of the levels of intensity involved in the project. By 10 hours after the shot, measured areas on YAG-39's decks had, in spite of the washdown, accumulated an average total dose of some 40 Roentgens. YAG-40's cumulative dose was 400 Roentgens, approaching a mean lethal dose. 15 hours after the shot, random sampling on YAG-40's decks still showed a dangerous 25 Roentgens per hour, while on YAG-39 it was only 2 Roentgens, a negligible rate by comparison. The weight of the spray assembly can be minor even for fighting ships, and the entire head of water can usually be handled by a ship's normal pumps. It is concluded that the washdown system can serve the purpose for which it was designed, to hold gamma radiation below decks of combat ships within tolerable levels in such fallout areas, and to hold weather surface contamination to levels permitting immediate topside emergency action after leaving the fallout. No thermal military effects tests were scheduled on Castle, but measurements were made of the thermal spectrum, power versus time, and total energy. Power versus time graphs show that the main thermal pulse of a low-yield weapon arrives and is essentially completed inside of a couple of seconds. From a high-yield weapon, it takes some 3 seconds to reach the peak of the main pulse, which has a comparatively long duration. Therefore, quick dodging, even into light cover, would allow target personnel to escape most of the thermal effects. This slower delivery time also requires a scaling up of low-yield thermal damage criteria. Equivalent damage from a 1 megaton bomb requires twice as many calories per square centimeter. The needed increase approaches 350% for 15 megatons and probably still more for higher yields. But even with these handicaps, the thermal destructive range of megaton weapons is huge. Against exposed troops wearing 4-layer winter uniform, an optimum burst height with a 100-kiloton bomb can produce 50% casualties out to nearly 2 miles, involving an area of 10 square miles. With the same 25-mile visibility, a 15-megaton burst will, even after tripling the calorie requirement, produce these 50% casualties out to the edges of a 75-square-mile area. Lighter clothes will greatly extend the area, and it should be remembered that far higher casualty rates will be produced nearer zero. Extending the comparisons, we see that the 100-kiloton weapon will probably cause heavy primary or secondary fire damage in average cities over about the same 10 square miles that fitted the 50% casualty probability. A great many small trash and litter fires would be initiated over some 25 square miles. Using the 15-megaton burst, we get very heavy fire damage over 75 square miles, and the sporadic small fire area may become in excess of 200 square miles. No estimate can be made as to how many of these fires would survive the blast winds, but based on Hiroshima and Nagasaki, plus test experience, destruction could be extensive. Tied directly to thermal effects of such magnitude is the high-priority problem of determining minimum safety parameters for aircraft delivering high-yield bombs. One channel of attack on this problem was the earlier work on means of delaying bomb burst until the aircraft reaches a safe distance. Drogue parachutes were designed for this purpose, to open after bomb release and slow the fall of the weapon. Still, it remained for Castle to derive more solid data as to what was a safe distance. The aircraft employed in the tests were a B-36 and one of our high-performance mediums, a B-47, from which extrapolations to the B-52 may be possible. On the B-47, primary interest was in the effects of radiant heat on the aluminum skin of the ailerons, 20,000th of an inch thick. A temperature rise in this skin of 370 degrees Fahrenheit over ambient was felt to be critical to the airplane's safety. The critical peak overpressure for the B-47 was considered to be 1 psi, and it was estimated that this envelope, as well as the gamma and gust loading envelopes, would lie well inside the thermal envelope at the chosen altitude of 35,000 feet. Instrumentation was extensive, primarily to measure thermal effects. A total of 43 thermocouples was installed at selected points in skin and supporting structure. Radiometers and calorimeters in the fuselage gave thermal time history and total input. Additional instruments included accelerometers, strain gauge bridges, pressure gauges, and numerous temp tapes attached to the skin. 6 cameras under the fuselage were aimed at zero to assist orientation calculations. A thermal shield was designed for attachment to the inside of the canopy of the aircraft to protect the pilot and co-pilot. For locating the test aircraft's flight positions, radar was supplemented by the accurate radist system, which used the heterodyning or phase relationships of radio signals from transmitters on the ground and on the aircraft. Participating on 5 of the shots, the B-47's flight pattern was selected to position it where it should receive the theoretical maximum allowable temperature rise, 370 degrees in the aileron skin. In practically every instance, the maximum skin temperature rise was substantially lower than predicted for the observed input, indicating that predictions of heat absorption and transfer and of cooling factors were conservative. Heat damage was in all cases minor, involving only some patches of blistered paint at various points. Because of the B-47's high escape speed, the highest overpressure recorded was around 1/3 of a pound, and the only blast damage was a split rubber coupling on the in-flight refueling manifold. On the B-36, also heavily instrumented, the maximum safe thermal level had been defined as that causing a 400-degree Fahrenheit temperature rise on the 20,000th of an inch magnesium skin under the elevator. This skin and other critical underside areas were white enamel coated to increase thermal reflectivity. 0.8 of a pound to the square inch was estimated to be the safe overpressure level, beyond which critical dishing in of bomb bay doors and buckling of skin might occur. The B-36's flight patterns placed it tail-on toward all but the last shot, for which it was flown head-on for both thermal and blast phases, with a sharp turn later to avoid the cloud. As a matter of record, no prompt gamma or fallout problems were encountered by either test aircraft. For the highest intensity thermal input recorded on the B-36, the skin temperature rise approached 260 degrees, 65% of critical. Predictions, especially for thermal response, were again generally conservative, with some inconsistencies. One effect observed was an abrupt momentary rise in jet tailpipe temperatures above the normal 500 degrees Fahrenheit. This appears to be the result of choking of the jet exhaust by overpressure and material motion associated with shock wave passage. However, no jet turbine damage was observed. At blast arrival on several of the shots, the B-36 reciprocating engines momentarily dropped and then raised their speeds by several hundred RPM before returning to normal. This was due to the engine torque balance being upset by the increased density and the gust immediately behind the shock wave. Visible thermal damage included some slight skin buckling on the elevators where white enamel had peeled or blistered, plus scorched enamel on some other areas. Some unprotected sponge rubber was burned around the lower aft blisters, one of which also developed cracks from thermal and or shock effects. Spotty blistering and blackening appeared on the radome. The highest overpressure reached the critical 0.8 of a pound level, with the average around half a pound. Blast damage included characteristic sheet metal dishing of wings, bomb bay doors, lower turret and landing gear doors, spotty rivet failure, and severe crushing of the radome. The highest gust loadings were on Shot 5, reaching 60 to 90% of design limit load at various critical stations. It is concluded that the B-36 can withstand the critical overpressure of 0.8 of a pound with some minor damage. However, with current delivery techniques, the B-36 delivering multi-megaton bombs will experience less than this overpressure. Another phase of the aircraft delivery problem was explored by planes fitted with gyro-stabilized cameras, which recorded time, azimuth, and tilt on a corner of their film. These aircraft, carefully positioned, took pictures of cloud rise and spread, primarily to determine their dangers to delivering bombers. Adding up the preliminary data from these successful projects, we find that both the B-36 and the B-47 can deliver weapons of the size tested on Castle with assurance of surviving the effects. Strategic Air Command bombers staging from Guam were also in the skies on the Castle shots because of continued interest in indirect bomb damage assessment, which was just one of many projects like long-range detection that we haven't time to look at in detail. While many phases of basic blast phenomena were measured on Castle, the projects were not on a large scale. In particular, structures testing was minimized for reasons of economy and lack of suitable sites. Bikini blast line instrumentation was in general of familiar types: air density and temperature gauges, ground baffle Wianco pressure gauges and accelerometers, dynamic pressure or Q gauges, and some gauges newly designed because of uncertainty as to the degree that existing Q gauges reflected dust loading of the air. It had been expected that wave forms from the Castle shots, largely propagated in cool air over water, would be clean and of ideal shape, but some records suggested dust and or water loading, indicating that the lagoon water was not a perfectly reflecting surface as had been assumed. However, the non-ideal behavior apparently did not significantly affect peak pressure levels, whose curves in general conformed well with standard cube root scaling theory. An interesting development on Shot 3 was a rainstorm, which at shot time apparently lay with one edge roughly over ground zero, which was in a cab on Enenman Island. Instrument readings to the east and west indicate that this unmeasured rain dampened peak pressure levels by approximately 15%, which is compatible with theory for a rain of quite moderate intensity. The real military importance of high-yield blast effects lies not in their quality or type, but in their enormous range compared to kiloton weapons. Defining blast range in terms of destruction may be more arbitrary than precise, but the Japanese surveys indicate that 8 psi, will destroy all wood frame structures, multi-story masonry wall structures, light steel frame buildings, and conventional reinforced concrete or brick buildings. This can reasonably be defined as severe damage. 4 psi will heavily damage portions of any normal building with near collapse of all lightly built structures. We will call this level moderate damage. A 100 kiloton weapon at optimum height will cause severe damage over an area of 5 square miles and moderate damage over 12 square miles. Contrast this, 5 and 12, with 80 square miles of severe damage and 240 square miles of moderate damage from a 15 megaton surface burst like Shot 1. 240 square miles, more than 20 Hiroshimas in a group, more than 10 Manhattans, in which blast compounded with fire may bring almost total destruction. An idea of the extensive damage that 15 megatons can do at still greater distances is obtained by a look at the Bikini Base camp on Inanman Island, almost 16 miles from Shot 1. The overpressure reached around 1.6 psi with a 12-second positive phase, and the area concerned in destruction of this order would be some 800 square miles, nearly 3 times the area of all the boroughs of New York City. Numerous secondary fires would probably aggravate the damage in any metropolitan area. Tree stand studies involved mainly stands of coconut palms up to 50 feet tall and stands of Pisonia, a native broadleaf similar to the American beech and averaging up to 80 feet high and 3 feet thick at breast height. Palm stand before and after pictures show almost half the trees broken by 4 1/4 psi. Here is a before picture of a Pisonia stand 12 miles from Shot 1, and then some afters. Overpressure 2.4 psi. Principal damage, crown and branch breakage, contrasted to the stem breakage characteristic of conifers tested on upshot knothole. Ground level measurements taken at intervals through a 2,000-foot stretch of trees indicated that even comparatively large tree stands will not reduce peak static pressures in the 4 psi region. Crater depth measurements made on Castle by sonic fathometer showed only the apparent crater depths, which may have run 30 to 50% less than the true craters, which were partially filled by disturbed earth and layers of water-drifted sand or mud. 14.5 megatons fired on a reef surface left a crater some 6,000 feet across. Estimated true crater depth, 240 feet. Note that the depth was only about 8% of the width. 130 kilotons fired on the surface of Inanman Island made a crater 700 feet across. Estimated depth, 75 feet. On small shots, the depth-to-width ratio seems to increase substantially. Here, a 6 megaton device was detonated at the surface of water 160 feet deep. The crater went 90 feet into the lagoon bottom and was 1,500 feet across. In general, the craters were broader and shallower than anticipated. While no rigorous scaling laws can yet be derived for application to land surface bursts in general, our crater prediction techniques were substantially improved by Castle data. A considerable grid of instrumentation was established in the Bikini Lagoon from 6,000 to 20,000 feet from zero to measure underwater pressure transmission. The pressure time gauges were suspended at various depths from moored buoys, some being self-recording and some sending data to large floating cylinders referred to as tuna cans. A number of the tuna cans telemetered data to an orbiting aircraft. The transducers or gauges were of several varieties: mechanical, electromechanical, and piezoelectric. The underwater pressures were of military interest from the standpoint of effects on ships, submarines, subpens, harbor facilities, minefields, and dams. The primary finding was that the pressures from a shallow water surface burst were about of the same magnitude as the air overpressures at the same distances, and are therefore probably of small military value. A related project was a study of minefield clearance, in which arrays of American and Russian mines were moored between 2,000 and 18,000 feet from a 6 megaton water surface burst. Only the American Mark 39 mines survived at 3,500 feet, while at 4,500 feet, the Russian also survived. About 60% of the older United States models survived at 7,000 feet, and no mines were damaged at 11,000 feet. It should be remembered that it took 6 megatons for these effects, and a 20-kiloton device might possibly not be reliable beyond 500 feet, though the scaling factors are uncertain. Instruments were set up on some of the Bikini Islands and coral heads in the lagoon to study water waves generated by the high-yield bursts. The waves followed normal shallow water propagation theory to a degree, but a number of anomalies of timing and amplitude remain to be explained. A 12-megaton shot in the northern lagoon sent water 5 feet deep over an island 12.5 miles away, 8 feet deep over one at 12 miles, and 10 feet over an island at 17 miles. Such waves, acting beyond the radius of strong blast effects, could obviously be very damaging to certain categories of shoreline targets. One aspect of the dynamic or wind pressure investigations on Castle involved exposure of groups of jeeps to what were expected to be classical or undeformed shock waves. Deformation of the shock wave from upshot knothole's low-height shot 10 caused substantial lowering of its static overpressures, but not of its dynamic pressures. Equipment damage was excessive for criteria based on the low static pressure, which is the usual parameter. So the question arose as to whether the dynamic pressure was an adequate criterion. The influence of the heavy dust loading of the air and of the blast's long positive phase duration were also in question. Jeep damage from Castle's relatively clean shocks correlated well with upshot knothole damage at the same dynamic pressures, so it is concluded that dynamic pressure is a valid criterion for damage to targets of this class. In summary, it could be said that Castle gave us more substantial knowledge of the possibilities of thermonuclear warfare. Ivy Mike showed us the outlines of that huge power, and Castle filled in the outlines, pinpointing great quantities of vital data. The finding that must be considered most significant is that of the thousands upon thousands of square miles that are made potentially lethal by wind-carried fallout from a multi-megaton surface burst.